Hello and welcome to Anyscale Connect. Today we're lucky to be joined by Archit Kulkarni, who's a software engineer at Anyscale. Archit joined Anyscale in 2020 after completing his PhD in mathematics at UC Berkeley. Among his other duties at Anyscale, he works on Restful, which is an open source library for serving machine learning models at scale. In his talk, he'll demonstrate some new features of Restful, including an integration with the open source machine learning lifecycle management platform, MLflow, as well as an easy way to use Restful to scale up an existing Python web server. With that, here's Archit Kulkarni.
Hi, my name is Archit Kulkarni. I'm a software engineer at Anyscale, and today I'll be telling you how to seamlessly scale your machine learning pipelines using Restful. So first, let's get started with an overview of Restful. And to put it in context, here's a summary of the machine learning lifecycle. So you've got the first phase, roughly, which is model development. And then you go into training. You're trying to get the best parameters for your model to make it the most accurate. And then finally, you have the third stage, which is inference, where you're actually trying to make predictions on the models. And that's where the end user application comes in. The end user is going to use your model to make a prediction. So in this talk, we'll be focusing on the last part, which is just inference. So Restful, in a nutshell, is a web framework built for machine learning model serving. It's a Python framework, and here's how something like this would look in Python. You'll have your machine learning model, and you can wrap it in a class. So in the constructor, you'll load your machine learning model, and this might take some time. Maybe you have to download a lot of data. And then when it's called, you'll pass in a web request object, and maybe that has some user input, some other data. Data comes in, you'll probably do some pre-processing on it because the model is going to want input of a certain form, maybe a tensor or a list of numbers or something like that. Then the model, you'll call predict on the model, and then finally you'll transform the output using some post-processing into a form that's more user-friendly. So let me give an outline of the rest of the talk. I'll continue with my overview of Restful and how it fits into the machine learning lifecycle. And then I'll talk about two integrations of Restful with other popular tools, MLflow and FastAPI. So first, let's talk about some of the requirements of model inference. So what is inference? Here's an example. You have an image and you want to know what the image is about. So maybe a machine learning model can tell you it's a cat. And so some requirements that you might want, and we'll go into more detail on each of these, are that your model inference solution is framework agnostic, and it supports arbitrary business logic, and that it's scalable. So let's go into the first requirement in more detail. So you want your model serving solution to be able to work seamlessly with multiple frameworks. So there are a lot of different machine learning frameworks out there, and they each have their pros and cons and specialties. Different architectures, different algorithms. But when you're solving a real world problem, you want to take the best solution that's out there, and you don't want to have to worry about whether it's compatible with the framework that you're already using. So ideally, your model serving solution should be able to just work with any framework. Another requirement is that your model serving solution should be able to support arbitrary business logic. And so that includes this pre-processing and post-processing that we were talking about earlier, because a lot of machine learning models will just accept a numeric tensor as input and will output another tensor list of numbers. And that's not very user-friendly. So you certainly want to be able to do pre-processing and post-processing. But even more than that, in a full practical application, you might want to authorize input, ping databases, or just you want the freedom to be able to do any kind of business logic that you want. So that's critical for a model serving solution. And finally, you want your model serving solution to, of course, be able to scale up your machine learning models. So that'll increase the speed with which users can make predictions and the number of users that can use your model. So for example, if you just had one machine running one replica of a model and you want to make a bunch of predictions on it, you don't want the predictions to take forever and pile up, because that's a pretty bad user experience. So in theory, a simple way to improve this is to have multiple copies of your models, so multiple replicas, all serving things in parallel. And while that can be kind of tricky to do, actually Restful makes it very easy. And we'll see an example of this later on in the talk. And on top of scaling, another requirement is batching. So you want your solution to support taking in batch requests. And, well, let me put it this way. A lot of machine learning models do very well with accepting batches of, say, 4 requests. And they'll be able to make those 4 predictions utilizing hardware concurrency and things like that. And it won't take 4 times as long as with a single request. There'll be some speed up there. So for the machine learning setting, you want to be able to take advantage of batching too. And finally, ideally, you want the flexibility to be able to use your model serving solution in multiple scenarios. And here's just a few. So one thing you might want to do is take your machine learning model and just run a single large job locally on your laptop or on some local cluster, just for your own personal use or for your experiment. Another use case might be you want to serve a model over HTTP, over the internet, to many public users. And those are kind of different scenarios. Ideally, you want to be able to support both. And also, you might want to use your model and integrate it with other services as well. So your other services should be able to query your model. And you don't want to have to make too many modifications to your code to be able to handle all these different kind of scenarios. So Restful meets all of these requirements that we talked about. So on the one hand, it's a high performance machine learning model serving library. It's framework agnostic, scales easily, and we'll see exactly how easy it is in our demo later. And it supports batching. And on top of that, it's flexible. So you can query your model from HTTP and also from Python using the same API. And this lets you easily integrate Restful with other tools. And what makes this possible is that Restful is built on a really useful distributed computation engine called Ray. And that means that as a user, even though you're writing a distributed application, you have all these replicas on all these different cores, all these different machines, you don't have to think about all the things that make distributed computing hard. For example, interprocess communication, failure management, fault tolerance, job scheduling. All these things are taken care of by Ray. And so that makes it a really nice experience for you, the user, to just write your code and then have Ray handle all the distributed computing issues. You just tell Restful to scale up your model, and it's as simple as that. So here's what the API looks like. And it's pretty similar to just ordinary functions and classes in Python. So you'll be able to serve any function or any stateful class that you want. And Restful will use multiple replicas to make copies of your model, and it'll be able to accept parallel requests, and that'll increase your throughput across cores on a single machine or across multiple machines on a cluster. And how you would actually query your model is you could do it in 2 ways. You can query it from HTTP, so using a route like this, and you can customize the route. Or you can query it from Python using what we call a served handle. And that's just an ordinary Python handle. And we call it like this. And one of the benefits of a Python serve handle, being able to just call your models from Python, is so that you can compose models in arbitrary ways. So oftentimes you're not just using one model in isolation. You might want to have a chain of models, each one doing a different thing, transforming the input in some way, and then feeding it into another model. That's represented by this chain here. Or you might have something that looks like this. Maybe you're doing A/B testing. You're sending some traffic from one model to another model and some to a second model. And you can think of even more complicated or convoluted ways of combining models. But the point is there's no limitations on that. Anything that you can code in Python, you can do using RayServe, because you'll just be able to query your models using a normal Python handle. And this also makes it easy to plug RayServe into other Python projects, such as, in this talk, we'll talk about Fast API and MLflow. But really, it's a great amount of flexibility. So let's start talking about our first integration, which is a new integration between RayServe and MLflow. So going back to the whole machine learning lifecycle that we talked about at the beginning of the talk, there's a lot that goes into it, and it's often difficult to manage all the complexity there. So for example, keeping track of experiments, your data is changing, your code is changing, they might live on your laptop or live somewhere else. It's difficult to keep track of dependencies. You know, if you want something reproducible, you want to send a project to a colleague, it would be nice if you could package everything together and just have them be able to run it. So MLflow is a tool for just simplifying the machine learning lifecycle and keeping track of all these things. So there's a few different aspects to MLflow. There's the tracking, so you can train your models and keep track of the runs, and keep track of the parameters and configurations all automatically with automatic logging. You can package them in reproducible formats with these MLflow projects, store all your models together in a model registry, and RayServe will come in at the last part, which is when you're actually serving the models. So let's take a closer look at what that looks like. So to get started serving your your MLflow models with RayServe, so this is assuming you've been using MLflow, you've trained your models, and now you're ready to deploy them in production. So they're already sitting in an MLflow model registry or something like that. So you'll install it as a Python package, MLflow RayServe. So just a deployment plugin. Call raystart --head. That starts a Ray cluster on your laptop, and you can also start a cluster. You can start a cluster on multiple machines as well. And then once your Ray cluster is up, call the command serve start. That starts a RayServe instance. And once that's set up, now you can call this RayServe MLflow API. So first I'll talk about the command line interface. There's also a Python API. They have the same features. But let's say you have your MLflow model and you just want to scale it up and you want to use RayServe to do it. So that's just one command in the command line. MLflow deployments, that's the API that we're using. We're going to create a deployment. So we're going to serve one model. -t RayServe, that's the deployment target. And then in here, we put the model URI, which is a reference to the specific model that you want to use. And give it a name, and then you pass in this configuration parameter. Various configuration parameters you can use for RayServe, like the maximum number of requests you want to use in your batch or whatnot. Here, we'll just use num replicas equals 100. So that just means I want to serve 100 replicas in my model all in parallel. In this model URI, this is where you actually pull the model from MLflow. And MLflow provides a variety of ways of storing your model. So you might have it in a model registry, in which case the URI looks like something like this. Or you might want to access a particular run if you were doing some experiment that has its own ID. Or you can also pull your model from some cloud storage. And then there's even more ways. So no matter where your model is saved, you'll be able to just plug it into RayServe using this identifier. That's the command line. And then on the Python side, you have the same features. This is what command would look like. And you'll just pass them in as parameters here. And the rest of the API on the command line side and on the Python side, you can create models, delete them, update them, everything that you would want to do to manage your deployment. So writing this plugin was quite simple. That's because RayServe is so flexible. The RayServe endpoints can be called from Python. And so integrating with MLflow, another Python project, was quite simple because you can just call the RayServe endpoint directly from the MLflow plugin. And it gives you a clean conceptual separation between two things. So RayServe just handles the data plane, the processing, and MLflow is in charge of the control plane. So the metadata, configuring your models. So really separating the computation from everything else means that RayServe is easy to plug into anything else. And while we're on the subject of MLflow, I'll mention another integration, this time involving RayTune. RayTune is a library built on top of Ray that is for hyperparameter tuning. So this is the training phase of the MLflow, of the machine learning lifecycle. So you can do state-of-the-art algorithms for hyperparameter sweep across multiple nodes in your cluster. And it's great because it'll automatically log all these runs to MLflow. And MLflow has a nice UI, which you can use to inspect all of these. And it's just a great way to keep track of everything. So now let's move on to the second integration I'll talk about, which is how would you use RayServe in conjunction with Python web framework, such as FastAPI. So first, a little bit about FastAPI, the modern high-performance web framework for building APIs using standard Python type hints. Super popular, very easy to use, and some of the benefits include automatic input validation, so you can just focus on writing your business logic. You don't have to worry about sanitizing the input or anything like that. Generates automatic documentation, and it's just really easy to use and easy to write bug-free code using FastAPI. So what's one problem you might have if you're trying to serve machine learning models? So maybe you have an existing Python web server, so FastAPI or AIO HTTP or any Python web server. And you're trying to serve some really computationally intensive machine learning model. And it's just too slow. You're getting too many requests, they're piling up, and it's a bad user experience. So how can you scale this up without starting from scratch or without finding a new solution? Well, the solution is to just keep the existing web server and offload the computation to RayServe. So because of the clean separation we were talking about earlier, this is pretty straightforward to do. And so let's jump right into a demo. So here's a really simple FastAPI application. And I'll walk you through it. So in the first line, we've imported FastAPI package. This is the FastAPI app. And now what we're actually going to serve is a pre-trained model. So, in real life, you probably spent a lot of time tweaking and training the model. Here, we're just going to use something off the shelf. So this is something from Hugging Face Transformers, and it's going to be a text generation model. And behind it, it's using OpenAI's GPT-2 text generation model. And what it does is you'll input a few words, maybe the start of a sentence, and then the model will automatically continue it into coherent English. And it's really amazing. We'll be able to see it in action. But also, this app is pretty simple as it is. All you need is one generate endpoint, and we've loaded our model here, and then the generate endpoint will handle GET requests to this URL. And based on the input query, we'll set it to output 50 words. So I've already started this running in the server. So let's just go ahead and run this command. So right now I've put in my query as machine learning is, and let's see how it continues that initial part. Okay, machine learning is one of the most, okay, it's all true, great. And we can keep doing it and it'll auto-generate using the machine learning model. And so one downside to this as it is it's quite slow. So I have some benchmarking code here, which is just going to generate a bunch of requests to this. And yeah, let's take a look at this. Okay, so it's taking a few seconds per query. So let me just cut this off before it gets to 100. So now let's see how we can scale this up and really speed it up using Reserve. So let me go back into the Fast API app, and let's start making some changes. So first, we'll need to import Ray and Reserve. Now, we need to connect to our Ray cluster. So there's already a Ray cluster running. So here's a dashboard where you can see I have various nodes. Each node has multiple cores. Nothing's happening on it right now. So on startup, we want to connect to this Ray cluster from our Python script. So in Fast API, this is how we handle a startup event. So this will just run at startup. All right, inside here, we need to call ray.init that connects to the Ray cluster. And then we want to start a Reserve instance. So this starts the Reserve client. And now we want to define a callable class that contains the model that we want to serve. So I'll just call it GPT-2. And we'll initialize it by just taking this initial isolation code and putting it inside the class. So now we have self.NLP model. That's just the model. And then when we call this class, this call function should take in request, which is a web request. And what we'll return is, well, okay, we're going to do the same query that we had before, but it's the member of this class, self.NLP model. And instead of query, it's coming from this web request, so that's request.data. So that's our class, and now we need to create a Reserve endpoint for this class to look behind. So let's call it client.create backend. Call this GPT-2, just a name for this backend. Pass in the class that we just created. And then as configuration parameters, let's set the number of replicas to be 10. Now let's create an endpoint to put this backend behind. Call it GPT endpoint. Name doesn't really matter. There's just one. And let's pass in the backend that we just created. And now, how do we actually call it? Now we'll use the serve handle API that we talked about earlier. So we'll get a handle to this endpoint. Of course, we can query it from HTTP, but we already have this Fast API web server that's handling all the HTTP stuff. We just want to use Reserve to offload the computation. So we'll get a Python handle to the GPT endpoint that we just created. And now we want to serve it inside the Fast API endpoint generate. We don't need this anymore. So we want to, this is how you call the serve handle. The .remote is just a reminder that it's a remote function. It's happening across many replicas. It's asynchronous, so you put in the wait here. And for this demo, if I want, let's just make this a global variable. So okay. Save. Here's my use-the-corn server. Let's kill it and restart it with the new main.py that we have. Okay, stuff we need to Put a colon here, no deal. All right, so while that's starting up, what did we build? Unicorn is running the Fast API app. Unicorn is handling the HTTP request and HTTP response. And then inside the Fast API, it's using the serve handle API to offload the computation to RayServe. And RayServe will manage all of the replicas. Okay, it's running. If I look at my Ray dashboard, I can see there's one replica sitting on one node. More replicas. So we're good to go. So let me now run the same benchmark that we had earlier. Since we have 8 replicas, let's use 8 simultaneous connections, just so we can really saturate our replicas. We need to pass in the query, of course. So let's start the server again. Okay, just wait for the startup. These warnings just mean there's no GPU installed, that's fine. All right, so now let's go ahead and run a benchmark. Okay, and you can see that it's much faster than it was before, right? And that's just because we set the number of replicas to 8. So these requests are being handled in parallel as we keep querying our endpoint. So this is great. Let's stop that. So I did run some tests on this earlier. So using a cluster with 8 machines and 16 cores each, here's the results. QPS is queries per second. So with one replica, it took like 2 seconds per query. And then if you multiply the number of replicas by 10, this throughput also increases by a factor of 10. The next multiple of 10, we don't quite get a 10x improvement. There's still only 8 machines, so the multi-core parallelism isn't as powerful as just having separate machines, but it's still quite a significant improvement. And of course, you can use as many machines as you like in the cluster. So to summarize, what did we do? We had a fast API app. It was serving a machine learning model that was really computationally intensive and so quite slow. But with just a few lines of code, we were able to make it much faster by using RayServe, letting it scale up the model to multiple replicas. All right, so in summary, RayServe is a high-performance machine learning model serving library. It has all these great features that it's framework agnostic, it's easily scalable, supports batching, takes advantage of high concurrency by having all these replicas to provide low latency for the user, and a bunch of other stuff that we didn't talk about. And on top of that, it's flexible. So we already saw in this talk some simple integrations with Fast API and MLflow. And RayServe allows you to serve arbitrary Python functions and classes. And this also means you can serve arbitrary Ray applications. So arbitrary, highly distributed applications, you can put them behind RayServe. And that's really powerful. So try out RayServe today. You can pip install RayServe, get started with the quick start on our documentation. And if you have any questions or you just want to chat about Ray, check out our forum at discuss.ray.io. And please reach out. We'd love to hear about your use cases. Some acknowledgements. I'd like to give thanks to Jules Damji, Sid Merching, and Paul Ogilvy from the MLflow team, and Simon Moe and Edward Oakes for helping out with this presentation, and the rest of the Ray team. Thank you very much.
So with that, we'll take questions. So thank you so much, Archit, for your excellent talk on RayServe, as well as some integrations with it, particularly MLflow. It was excellent. So let's start with questions.
Thanks, Michael.
Mhm. So the first question is it possible to use Spark NLP pipeline inside Fast API?
Right. So I haven't used Spark NLP pipeline before, but it looks, from what I'm seeing online, it looks like you should be able to just wrap it in a Python class similar to what we did in our demo. And Rayserve is so flexible that any class where you can load the model, like in the init function, and then serve it in the call function, it should work pretty much the same way. So I imagine that you could use it inside Fast API and use Rayserve to scale it up.
Oh, wonderful. So the next question is, since Rayserve also gives an HTTPS endpoint basically out of the box, is there a reason to use Fast API at all in the example presented? Would it just be better to only use Rayserve?
Yeah, good question. So you're right, this example could have been done just with Rayserve because Rayserve comes with an HTTP server out of the box. This example was sort of for the perspective of someone who was already using Fast API or was using some advanced features of Fast API, and they just wanted to increase their throughput. And so it was to highlight the way you can separate the computation from the HTTP serving and offload the computation to Rayserve. But you could totally have done the example just with Rayserve.
Okay, so in your example, where is your Ray running? A local machine, a Kubernetes cluster, or a cloud cluster?
Yeah, great question. I probably should have mentioned this in the talk. So it is a cloud cluster. It's actually running on the Anyscale product. So it made it very easy for me to just start up the cluster using a Ray Docker image with everything pre-installed. Yeah, so it's a cloud cluster on AWS, I believe.
Okay. So we don't have a ton of questions, so everyone feel free to ask a lot of questions. Just in general, how recent, this is my own question, how recent are the MLflow integrations?
Yeah, we started working on these just in the last couple of months, and they're ready to go. So we're excited for people to try them out. Yeah.
Okay. So some other questions are, so what's next for Rayserve? So you've introduced a lot of new integrations, a lot of new features. So what's coming next?
Yeah, that's a great question. So one of the things I'm working on is getting Rayserve to more closely integrate with the Anyscale product. We're also really trying to get Rayserve being adopted in production. And so we're very eager to hear from users about their use cases, so we can, build features for Rayserve to cater to those needs.
Okay. So next question is more just like comment, but I figured I'd ask it anyway. So someone said, excellent work. We're using it internally. So they've integrated with MLflow with Ray on their own a few months back. But now we're using your implementation. So your work has, been used, which is wonderful. So is there documentation somewhere for these integrations?
Yeah. So first of all, yeah, Harvinder, that's great to hear. And if you do get a chance to try out the MLflow Rayserve plugin, please let us know your thoughts. Yeah, it's I guess it's the first release, so there's definitely improvements we can make. Yeah, as for the documentation, rayserve.org, you can also just Google MLflow Rayserve. The first result should be the GitHub page for the MLflow Rayserve plugin. And that should work out of the box. But yeah, let us know your experience with that, and we'd be happy to help you out.
Yeah, I've also noticed there's a blog post on Ray and MLflow that was released relatively recently from Googling during this presentation. So the next question is, what's the timeline for releasing Rayserve 2.0? Relatively speaking here.
Yeah, well, so Ray's continuously improving, and the release cycle is tied to the Ray release cycle. So Ray 1.2 just came out. Yeah, so Rayserve 2.0 no specific timeline, but we do release new Ray versions and versions of all the Ray libraries every, say, 1 or 2 months.
Okay, we always check the release notes as well,
Yeah.
and ask in Slack and
Yeah.
discuss and such.
Yeah.
So the next question is from Andre on how do you specify the MLflow tracking server URL? So is it through an
Yeah,
environment variable or something?
right. Yeah, so we're working with the MLflow team on this. But yeah, so we'll get back to you when there's a fix for that. So maybe yeah, there should be a fix for that very soon. But yeah, we're aware of that issue.
Okay. Sure. So, I mean, someone asked a question. Can I ask a Ray Tune related question? So would that be okay with you?
I'm not a Ray Tune expert. We can, you can, yeah, feel free to ask, but I probably won't be able to answer.
Okay. We also probably have other experts here. So if you ask it, we'll probably find a way to find a solution. So another question is about what's the major difference between ML Serve and other RESTful services offerings?
Yeah, good question. So the machine learning models are very computationally intensive. That's, I guess, one difference. Yeah, so sort of some of the requirements that we highlighted in the beginning of the talk, you want it to be framework agnostic, you want it to support batching. There's certain things like this that are more specific to machine learning models. Another thing is your machine learning models are always being updated and so on. So the deployment is maybe more dynamic than a non-machine learning service application.
So the next question is, does Ray handle container provisioning, or do my containers need to be available in advance?
So this question, I'm not actually sure about the answer to this. Maybe I'm sure people would be able to help out on the Ray forum.
Yeah, they're pretty useful. So the next question is, are there plans to integrate with managed machine learning services like GCP's AI platform?
I don't think there are any plans along those lines at the moment, no.
Okay. One thing also just to mention is that if people have questions about anything Ray related, because this is a very big sort of project. Ray project is a massive project. There's Ray Serve, there's Ray Tune, there's libraries for reinforcement learning and more. Always feel free to ask either here in the Slack channels or under discuss forums, because there's a lot of experts in various different forums you can get your questions asked and answered. So does anyone else have more questions as we continue? One thing I also, we have more questions. So the next question is, can we pass class methods inside tune.run arguments?
Yeah, I think that might be a question for discuss.ray.io, the Ray forum or the Ray Slack. Yeah.
So the one thing I also like to mention here is that we have discussed, we have Slack, but you can also send us a message through events@anyscale.com, and we can answer questions about future events, upcoming things we have going on. I also like to mention that in a couple of weeks, we will have Ray Summit. So you can submit your talk now, and the call for proposals closes on February 24th. So we'd love to hear your talk. We'd love to have you at the event, because you can learn so much about Ray and the different use cases. I'll check to see if we have more questions. And if not, then we'll go from there. Okay. So are you okay with answering another like 2 or 3 questions?
Yeah.
Okay, wonderful. Yeah. So the next question is there a best practices guide for maintaining and updating models of production without downtime?
So in the Rayserve documentation, there is an example, a sample code for behind one endpoint switching from one Rayserve backend to another without downtime using some of these advanced features like traffic splitting and so on. So you should be able to find something useful there, but please let us know if we can provide more help there.
So the final question, and I really appreciate all these questions, is can I integrate my Rayserve within a Flask app as well, like you did with Fast API?
Yeah, the same thing should be possible. So it's very general, right? You have your Python class and your serve handle, which you query from Python. So I don't see any roadblocks there. Yeah.
Okay, and I promise this is the final question because people are very interested in integrations with Rayserve.
Mhm.
So can we put Fast API plus Ray code in a container and publish it in Azure Web App?
So I'm not too familiar with Azure Web App. But I mean, I don't see any reason why something like this shouldn't be possible to put this code in a container and serve it from there.
Yeah, Rayserve is very flexible. So just about anything you want to productionalize, Rayserve can help, or there will be some way to make it work in some way. So that's it for questions. I want to thank you so much for giving the talk, taking time to work on it, as well as answer all these questions from a vast variety of use cases. So thank you, Archit.
Thanks. Yeah. Thank you. Yeah. Thanks everyone for watching.